Alright, let's look at initial value problems here for a bit. Basically, this is a nice application of antidifferentiation. So here's our, let's just proceed by example. Suppose you know the derivative of some unknown function f is equal to, gee, I don't know, how about x plus e to the x? And suppose we also know that the value of the function at 0 is equal to 0. Our goal then, our task, if you like, find f of x, all right? Now, so apparently f is a, an antiderivative of this function, right? So that suggests that f of x is equal to 1/2 x squared plus e to the x, right? Because if I differentiate this, I get back x and I get back e to the x, right? So I integrated this to get that. But then to be fair, I have to say plus some constant. I don't know what the constant is yet. But then the thing is, this isn't just indefinite integration. This time I'm given this extra piece of data, right? The so-called initial value. It doesn't have to be at 0. I just did 0 to keep it simple here. I'll do the next one at something other than 0. So f of 0 is 0. And so then all you got to do is just plug in the data into the general antiderivative that you got here, or the indefinite integral if you like. So f of 0 is 1/2 0 squared plus e to the 0 plus c, which is, by the way, 1 plus c. Now that's equal to 0, so therefore c is equal to -1, and there you have it. We found the answer. F of x is equal to 1/2 x squared plus e to the x minus 1. So there is an initial value problem. Let's look at another example. Example 2. Suppose that you know that df dx, right, is equal to sine of x plus cosine of x, all right? And suppose you also know that f of pi, let's say, is equal to 3, all right? Find f. Okay, so, I mean, graphically, it's kind of fascinating what we're doing, right? So, like, basically we're saying, I know one point on the graph of f of x, 3 comma pi in this case, so it's like, it's here, right? And I'm given that the derivative function is sine plus cosine, so I won't try to graph it, but, that's given. So this is enough information to take this one point and create the whole curve, right? It's kind of cool. Right, anyway, so here goes. F of x, I'd take the integral of this, I get what? I get minus cosine of x plus sine x, right, plus a constant. But I know that f of pi is minus cosine pi plus the sine of pi plus c, right? But of course sine of pi is 0, cosine of pi is -1, minus 1 gives me +1, so I've got, what do I got? I got c plus 1 equals to 0 then, so therefore c is -1. c is -1 again, that's a total accident, I'm sorry, that's funny. That's my luck. So the answer then is f of x is equal to, looks to be sine x minus cosine x minus 1, which I don't know. I'm not going to try to graph it. Okay, I have to think about that for a little bit to graph it. This could be rewritten as a single sine function shifted. Hopefully I'll show you how to do that in a later video. Now, of course, the main application for the initial value problem comes to us from physics. In physics, of course, this is a pretty standard example. I'll do for this standard example for you, and then we'll call it quits for this and shift over to U substitution. But example 3, if I know that the acceleration, right, is equal to minus g, and if I know that, say, y of times 0 is equal to y naught, and the velocity at time 0 is equal to v naught, then find y of t, right? Y is a function of time. So this time, acceleration, we need two initial conditions, right? So this is a two-step calculation. First of all, we solve the initial value problem for velocity. So we have dv dt, right, equals to minus g. So that tells me that v of t is equal to minus gt plus some constant. Let me call it c1. All right, now we'd be stuck, except that we also know that velocity times 0 is v naught, right? So v of 0 is v naught, but it's also equal to minus g times 0 plus c1, so therefore c1 is v naught. So there you go. The velocity as a function of time is in fact v naught minus gt. All right. Well, that's great, but that's not what we're after. We want to find y as a function of time, right? So, great. This is equal to dy dt. So I solve another initial value problem. This time integrate this again. That gives me y of t is v naught t minus 1/2 t squared, gt squared I should say. There's a g here. Minus 1/2 gt squared plus c2. But I know that y of 0 is equal to y naught, and that's equal to v naught times 0 minus g over 2 times 0 squared plus c2. Therefore, c2 is equal to y naught. And we conclude with the well-known formula for a object falling under the constant acceleration of gravity. Now, we differentiated this thing before, but now I showed you how to get from the acceleration being constant back to this formula. Before I just started with this formula and differentiated it, right? So here it is. So that, folks, is the initial value problem in a nutshell. You know, from another perspective, congratulations, you just learned how to solve differential equations. Each one of these is a differential equation, and we solve them. In fact, this is a second order differential equation we just solved. These are first orders. But anyway, more on that in a later part of Calculus 2. We'll talk about differential equations in a little bit more generality. All right, so next up, U substitution. Thanks.